and I guess these are symmetric functions which let me find my notes, in two sets of variables. F, and then there are two sets of variables, we write it like this. They are symmetric in x, symmetric in y. So this x just signifies x1, x2 and so on, this signifies y1, y2 and so on. And then if you put y1 equal to minus x1, then the dependence on x1 and y1 goes away. So those were the supersymmetric functions, and a very nice example is given by these functions ek xy, which is summation which is defined by summation ek xy, k goes from 0 to infinity, k q to the k is product I goes from 1 to infinity, 1 plus xiq by 1 minus yiq. So you see, if you put x1 equals minus y1, then these first terms will cancel out. And so these are the elementary symmetric functions, and then you using a 2D type determinant, you can define the super Schur function. So S. So what does H stand for? Hook, hook. So they are also called hook Schur functions, and Hs lambda xy is defined as the determinant of E lambda prime I minus I plus j. And she proved a very nice formula for these things using Plethism, which was that Hs lambda xy equals S lambda Plethism x minus py evaluated at p equals minus 1, right? Okay. So that was a summary of some of the things that Nishu did last time. But there was another description of these super symmetric Schur functions, which was in terms of certain tableau, which are called superstandard tableau. So I will come back to that in a minute, but what I want to do today is give a yeah, this is in xy. So these are the super elementary symmetric functions ek xy, and when you have no y variables, then these actually become the elementary symmetric functions. So that's one thing to be noted. When there are no y variables, this just becomes the ring of symmetric functions, and whatever theory you do should sort of specialize to the theory of ordinary symmetric functions when you have no y variables. So even this hook Schur function, when you have no y variables, it will just become the complete symmetry. No, it will become the Schur function in the x variables. And
What do you mean by x minus py?
Yeah, that's all very difficult to explain. So no, but let us not go into that, because I think yeah. So it is something defined axiomatically by axioms of Plethism, which we need to write down clearly. Yeah. Maybe we will discuss that another day. I really, because we started this last time and it sort of, yeah. Huh? But she explained what it means sort of, but anyway it's not going to play much of a role in today's lecture, so let's leave it at that. There's another thing, I think Nishu, correct me if I'm wrong, so there's an omega on this, right, and omega s lambda of x y is yx.
You are defining the ring of supersymmetry.
Yeah.
Then omega of h is lambda.
Yeah,
Is
is hs lambda,
prime of y.
but it's also yx, no, lambda prime of y, no, lambda of yx, and that's the same as hs lambda prime of xy, I think. I'm just guessing all this, yeah. Oh, CMI is here, yes. Okay, so the nice thing about the supersymmetric theory is that it behaves very beautifully with respect to this involution omega. It's a theory that is somehow much more symmetric with respect to omega than the theory of symmetric functions. So let me elaborate on that. So if so in my book there are these well, okay, it's they're everywhere. There are these representations called permutation representations of Sn whose Frobenius characteristic is h lambda, and their twists by the sign have e lambda. So there's a way to do this to do this in a symmetric way where you don't prioritize h lambda or e lambda, but sort of take them both together. So the question is, so we have these representations. So this is you know, I'll also, and then we have, so this is a permutation representation. This x lambda consists of set partitions of shape lambda. I'll come back to that in more detail later. And this epsilon denotes the sign representation. So there are these two representations. This guy has Frobenius characteristic h lambda. This has Frobenius characteristic e mu. So these are often called u lambda. And so what I want to do, it's very natural to kind of try to mix these up and get a representation whose Frobenius characteristic will be h lambda times e mu. So the obvious thing to do that, so I'll just introduce some notation. N denotes non-negative integers. N will be broken up into a sum k plus L, and D will be written as R plus S. So this, in Schur-Weil duality, this N is the Cn and this D is the Sd. So the GLN and Sd. So both of them are broken up, and we look at mu to be an integer vector mu1 up to mu k. So this is, sorry, mu k, no, mu, damn it. So in Schur-Weil duality we look at, yeah, they must add up to, nu s, this is in n to the s. So these are just integer vectors, or you can think of them as weak compositions, and we'll have the property that the sum of the entries of mu is k, the sum of entries of nu is s. KL, yeah, right. And so we'll define now this representation which we want. it should have Frobenius characteristic H lambda E H mu E nu. So I'll call it U mu nu is int S R cross S S to S D, and then on the S R you take just the representation C x mu, and on the S S, so this is a tensor product, but it is not the Kronecker tensor product, it gives a representation of the product group. And this thing has Frobenius characteristic H mu, this has Frobenius characteristic E nu. So the characteristic of U mu nu is equal to H mu E nu. Okay. So yeah. No. Sorry, this should be, forget about this n here, this should be SD. Let's not, there's no Sn. Let's say lambda is a partition of T. So this is, there's no Sn anywhere in this picture. N is k plus L, so that's like the number of variables. So you have k, Vishwanath would say bosonic variables, and n fermionic variables, right. So, and yeah, L, k bosonic and L.
Bosonic is just the H.
H and E, yeah. So, yeah, so this is the thing. So, there is also some sort of version of GLN hiding behind all this. But it's called super GLN. It's not a group. It's algebra.
Mu is a representation of what?
SR. Mu is a partition of. Oh, mu should be a partition of R. Wait. Yeah. So that's what I thought. Maybe I messed this up. No. So I want this for sure. So I think this should be. I was hesitating earlier, but sorry. Yeah, that makes more sense.
But it is now a composition.
What?
Okay.
Yeah. So let me explain what this X mu is. It's all set partitions S1 union Sk, which should be a set partition of the set R. Such that Si is equal to mu I. No, I want it to be an integer vector.
But I mean, ultimately this is indexed by mu and nu partitions. It's isomorphic.
No. It's isomorphic if you
Right.
permute the
Yeah,
things.
so
Yeah.
if you just take the equivalence classes.
Yeah, that's true. So, okay, so I hope now this everything looks correct. Yeah. Okay, so this is X mu, and similarly X nu. So SR acts on X mu, and X nu is similarly a set partition of S, and so SS acts on S nu, and so it's kind of Satish is here. Okay, so I don't know if I can hear him, but he's connecting to audio.
So is there a n equals to k plus n? Is there a, does it play a role here? N is equal to k plus n.
So you can just start with K and L. Yeah, it doesn't matter. N is the sum. Yeah. So I Satish just joined. So maybe I'll just say what I was doing. So we just started, so this is, you can ignore everything but just start from here. So we have two integer vectors, mu and nu. Mu is sums to r, nu sums to s, and we construct a representation whose Frobenius characteristic is h mu e nu. So somehow you construct this representation whose Frobenius characteristic is h mu e nu. So that's all we have done till now. Okay. So so now the question is, how does this decompose into irreducible? So what is the analog of Young's rule, right? So remember Young's rule. H lambda is equal to summation, maybe I should say H mu is equal to summation over lambda k lambda mu s lambda, where k lambda mu is the number of semi-standard Young tableau of shape lambda, and weight mu. Right. So here is the question, what is h mu e nu? So what are these coefficients? Now we are only working in ordinary symmetric functions.
No, E is also you have to write in terms of.
Yeah, so E nu is summation lambda k lambda prime mu s lambda. So what is this? So that if you ask this question, the answer comes, the notion of a super standard tableau comes about very naturally. So super standard tableau of shape lambda and weight mu comma nu. So this is what I want to define. So what you do is, you take a Young diagram, and you fill it with letters. There are two kinds of letters. So there are letters with alphabet is 1, 2, 3 up to so alphabet, in this context it should be 1, 2, 3 up to k, and 1 prime, 2 prime up to L prime. So here let me give you an example. So you can do 1, 1, 2, 2, 2, 3, 4, 6. So this is the unprimed letters. It is just a semi-standard tableau, and then the skew shape that's left, you make it a row strict tableau. So you put you can do this 1, 1, 1, 1 prime, 1 prime, 1 prime, 2 prime, let us say 2 prime, and then 1 prime, 4 prime. So this is a super standard tableau. So the rules are, you have 1 less than 2 less than 3 less than k less than 1 prime less than 2 prime less than L prime, weakly increasing along rows and columns, then column strict in the unprimed variables and rho strict in the primed variables. And then we will define a Koska number corresponding to this, k lambda mu nu. This is the number of superstandard tableau of shape lambda and weight mu nu. So, now you see that if nu is trivial, then this is just k lambda mu, and if nu is trivial, this is k lambda prime nu, because we have changed column strict to row strict, right. So, let me write that down maybe. So, yeah, let me write it down in fact. So, k lambda mu mt is the ordinary Koska k lambda mu, k lambda mt nu is k lambda prime nu. So, it gives a symmetric thing, it includes both k lambda and k lambda prime as special cases. So, it is again symmetric with respect to this involution. And so, here is the statement. What?
So for k lambda mu nu,
1. Huh?
So you want mu and nu such that mu plus nu prime is lambda or mu plus nu is lambda?
What mu plus size of mu plus size of nu is lambda, size of lambda. And this one was R and this was S, right, and this had K parts and this had L parts, and totally the size is D, where lambda is a partition of D. Yes, this theorem, what is just Pereira?
No, meaning starting from h mu is k lambda mu s r.
Correct, exactly. So, theorem or whatever, and as Aritra says, it is just Peary rule. So, h mu e nu is sum over lambda k lambda mu nu s lambda. So, you can prove this using the Peary rule. Let me just do that. It just kind of follows more or less straight away. So, we will prove it by induction on L. L is the number of parts of nu. So, what do you do? So, you have h mu. So, let us say nu tilde equals nu 1 up to nu L minus 1. Then h mu e nu tilde is summation over lambda k lambda mu nu tilde s lambda. So, now h mu e nu is h mu e nu tilde times e nu L. So, this is just sum over lambda k lambda mu nu tilde sum over eta such that eta minus lambda is a vertical strip of length nu L s eta, right. And so, now you collect write it as a sum over eta. So, the sum over eta, and then you have sum over lambda such that eta minus lambda is a vertical strip of length nu L, here S eta k lambda mu tilde. But this is the same as k eta mu nu S eta, just because if you have a lambda such that eta, if eta minus lambda is a vertical strip, you just put L prime in all those new boxes, and that will give you a semi standard Young tableau of shape eta with weight mu nu. So that's the proof, as just of course the base case is nu is empty, it's already stated there. So that's one way of thinking about this. And so now you can define, as in Mathes's book, you can define the super Schur algebra in analogy with the way he defines the Schur algebra. So how do you define the Schur algebra? S and D is usually defined to be end of SD, direct sum of lambda belongs to n to the n, size of lambda equals d, C of x, let us just say mu. Okay. So this is the definition of the Schur algebra, one of the definitions of the Schur algebra. Right. So we can do the same thing and define the super Schur algebra. No, it's actually, I'm saying integer vector, not partition. Yeah. So another definition is partitions with at most n parts. Those two rings are Morita equivalent but not isomorphic. If you replace integer vectors with integer partitions, then you get a Morita equivalent algebra, but they are not isomorphic. So that's so we can define now the super Schur algebra. S K L D is end S T So here mu is a vector with k parts, nu is a vector with L parts, and so on. So in the classical theory of Schur algebras, the modules for these correspond to polynomial representations of GL and C. So there is some analog of this, maybe I will try to explain it some other time, but I have only part of the thing. So here's what you do. So then the theorem, so we can ask, okay, so what do the simple modules of this look like, right? So well, so if you want to know the simple modules, so suppose you have a group G and you have some representations Vi raised to the power mi, and you look at this, these are simples, and you look at this, right. So this is an algebra A. Then what happens is that this algebra A becomes sum over I m mi by mi matrices of this right, those multiplicity spaces. And so what that means is that the irreducible representations of A are actually c to the power mi. So, if you write wi to be c to the power mi, and by that I mean this, the c to the power mi that is here, then these are the simple A modules. So, what you get is that the A modules are in bijection with the simple modules which are in the decomposition, and the dimension of the simple module is simple A module is the multiplicity of the irreducible G representation. So, just apply the same principle here. So, what you have to figure out is what are the simple what are the representations of SD which occur in K mu nu. Okay, I have a question, I do not know if Nishu figured it out or not. So, there is one more statement that K lambda mu is positive if and only if lambda is greater than or equal to mu in the dominance order. So, I was not sure what the exact statement here is. Did you figure it out? No. Okay. So, if anybody can give me the answer to this, should be some sort of mixed thing. So, let us look at one more example where say this mu and nu have only one part. So, let us look at what is the meaning of M. Mu is a partition of R, nu is a partition of S. So, well, how do we get a handle on this? Well, what we need to do is look at HRES, right. But from Peary's rule, you know what this is. You know that this is S R plus 1, 1 to the power S plus S R comma what? No, 1 to the power S minus 1. S R comma 1 to the power S. They are just two Schur functions, right. So that is a nice example. So the only things that occur are hooks, but not even all hooks occur, only two of these hooks occur. So, so whatever answer you find to this question should also take this example into account. So, can you guess what the simple SK modules, SKLD modules? Well, they are in bijection with partitions of lambda, but not all of them. Such that lambda k plus 1 less than or equal to L, the module W lambda corresponding to lambda has dimension k lambda. So, this is only just following from figuring out these decompositions. So, we already know that it should have right. So, because let me just no, sorry, sum over all mu nu. Where mu has k parts and nu has L parts. Well, this follows essentially from this statement here, right, because what we are saying from that statement is that U mu nu has decomposition as a representation of ST has decomposition k lambda mu nu S lambda. So the only thing to be proved here is that k lambda mu nu is positive if and only if this condition holds, lambda k plus 1 is less than or equal to L. So it suffices to show that there exists mu nu such that, show that given lambda there exists mu nu such that k lambda mu nu positive if and only if this lambda k plus 1 is less than or equal to L. Let me give you the geometric. Nishu talked about this last time. What is the meaning of this condition lambda k plus 1 is less than or equal to L? Just means that this lambda, its Young diagram fits inside a hook shaped region. So let me draw that maybe over here. Hook shaped region. So you take here K and you take here L and you take this region . So what is lambda k plus 1? This is lambda k plus 1, right? And you are saying that lambda k plus 1 is less than or equal to L. So for lambda 1, lambda 2 up to lambda L we have no restriction, but after this all these columns should be inside, should have at most, all these rows should have at most L columns. So we are saying that this Young diagram, whatever it is, sits inside this hook shaped region. There is no restriction on, there is a chat from, so Satish says one could think of H mu E nu as a skew Schur, is that right? So is this a Littlewood Richardson coefficient? Is it a Littlewood Richardson? I don't know why. Which Q Schur is it? You can just unmute and talk.
I mean, HR times CL.
Huh.
It is Q Schur.
No. Okay.
I mean, you can think of that as trivial, then always find a solution with R, a row has R, it works as under R.
I don't see it. Anyway, maybe. So this is the picture. These are the lambdas, and Satish is not saying anything more. Okay, so. Oh yeah, yeah. Do I have to unmute him or something? Oh, then what's the use of raising his hand? Oh, wait. Okay. Ah, there he is.
Oh no, I think there was some technical mistake.
In unmuting or in H mu in you?
I think raising hand. No, I had to go out and then come back.
Oh, okay, okay. Yeah, so no, I was just wondering about how H mu in you is a skew Schur function.
Oh, okay. So Hn is a row, right? Is skew is fillings of a row, and then you just take disjoint products of rows and columns. You get H times E.
No, it is not a single element.
I mean, if you want to take H2 times H3, then you just take two columns, two rows of one of size 2, one of size 3, and then take the disjoint product. You get a skew shape. Am I making sense?
It's a generalized little bit.
Yeah, everything is a generalized little word, right? Because H and E are Schur functions, HK and EL are Schur functions. So, yeah.
Right.
Yeah.
Right.
Oh,
What is it?
this little, no, he just wants you take disjoint rows. Take
Yeah, got it, yeah.
like that, disjoint rows and then
Disjoint column, multiply them all. Yes, it's that way. It's a product of many Schur functions.
No, but then if you think of the overall thing,
It's one skew Schur function.
Huh?
think of that overall thing as a single shape.
Oh, so what he's saying is I will take like this.
Right. Right.
Is that right?
Yeah. Right.
Then tableau on this is just you can independently fill each other.
So, but for not for E nu. So E nu I is not a Schur function.
It is E of a column, right?
Of a column, not of a row.
But it's still a Schur function, right? It's S of a column.
Yeah, then
So these things are, these vertical things are there. It's a nice observation.
Like a multiple LR coefficient is a single LR.
Yeah, that means a multiple LR quotient is single LR. Yeah, it's a good trick to know, I guess. Yeah. Okay, so let's see. So so that's all I have to prove, that this thing, and that's easy to prove. So firstly, so I need to show that this thing, right? So first let's consider the case where, so I have to prove two ways. So firstly, suppose k lambda mu nu is greater than 0, then I want to claim that lambda k, now look at the k plus first row here, right? So all the elements 1 to k will go into the first k rows, because it's a semi-standard Young tableau, and the alphabet 1 to k, the columns are strictly increasing. So all the i's are in the first I rows. So all the numbers 1 to k go in the first k rows. So the numbers from 1 prime to L prime, they will start, they will, yeah. So the only numbers in this L plus 1th row are the numbers 1 prime to L prime, nothing else is allowed, right? But that has to be strictly increasing. So it cannot be more than L prime in L in length. The longest you can have is you have all the numbers from 1 to L prime. So that's it. Okay, so I don't know if I should write anything, because L plus K plus first row has 1 prime to L prime strictly increasing. Has a subset of 1 prime to L prime. Okay, so what about the converse? If lambda k plus 1 is less than or equal to L prime, then I must find mu, nu and a super standard tableau, right? So, so what I will do is I will just take this thing to be mu. Yeah, yeah. What is this? Something is very confusing. So, I will take this to be mu, I will take this to be nu prime, and then I will put 1s along the rows here, 1s on the first row, 2, 2, 2, 2, 3, 3, 3, 3, and here I will put 1 prime, 1 prime, 1 prime, 1 prime, 2 prime, 2 prime, 3 prime, 3 prime. So, this, as Aritra said, the super standard tableau, and you get this. So, that is it. So, that is the main theorem of today, that is proved. Okay. So then this this thing is called the tensor space. So, super tensor space.
So said if k lambda mu nu greater than 0, lambda k plus 1 less equal to L prime.
Yeah.
And if lambda k plus 1 less equal to L prime, then you are constructing a.
Yeah, so what you can do is you just take mu to be this, since mu has at most k rows.
Oh, so you are selecting a mu.
Yeah, I am taking mu to be everything in this part.
Right. So, okay.
Yeah, you could do it another way, you could take nu prime to be everything in this part and mu to be what is to the right.
Right. So, the other direction is there exists a mu and mu such that.
Yeah. So, my main question is, what is the positivity condition for this super standard Koska coefficients? Okay. So, yeah, then I have some other stuff which is kind of speculative. Yeah, okay, oh yeah, no, but there is one more thing which I can say. Yeah, so let us come to that. So, there is an alternative description of this tensor space. So, for that I need to just explain this notion of twisted permutation representation. So, what is a permutation representation? You have this group G acting on a set X, and then you look at the complex valued functions on X, and that becomes a representation. Now, what you can do is you can try to twist this action by some scalar. So, what you want to do is you want to put some scalar alpha gx over here. So, what is the condition for this to be a representation? So, you require that alpha of 1, this is just a normalization, x is equal to 1 for all x in x. And if you want this to be a group homomorphism and just work it out, what you will get is alpha gh x is equal to alpha gx alpha h g inverse x. So, I will call such a function a twist. So, alpha is just a function from g cross x to C star a function from G cross X to C star satisfying these two conditions, I will call it a twist.
Is this a projective representation?
No, it is an ordinary representation. So, a simple example is firstly just a permutation representation where you take the twist to be 1. But you can also take the permutation representation and twist it by a character of the group. In that case, the twist depends only on G and not on X. But what we need for our this thing is a twist which depends on G and X. So, and this is leads us to the definition of this tensor space, which is in Berel and Regev's paper. So, probably, yeah. So then that becomes you get a twisted, you get a representation of G, you get what is called the twisted group algebra or something maybe, but I am not sure. Okay, so you can work it out. I called it a twist. I am sure there is, yeah. So, yeah, I was tempted to call it a co-cycle, but then I thought it will cause confusion. So, I just called it a twist. So, this looks like a co-cycle. What is that? One co-cycle condition, right? Two co-cycle. Okay. Something.
No, that would imply it is projective representation.
No, but this is an ordinary representation. Yeah, I mean one can think about this. So now the thing is, so we will call this representation twisted representation Cx alpha, twisted permutation representation. And this u mu nu is actually a twisted permutation representation. So, twisted permutation representation. Yeah, I will tell you. So, let us do an example. I want to reconcile this definition of tensor space I have given with the one in Berel and Regev. So, X mu nu equals set partitions S1 union S. Remember, mu had k parts and nu had L parts. And this has to be a set partition of D. These things can be empty also. Then define epsilon G X. This is going to be my twist to be minus 1 raised to inv Gx, where inv Gx this thing is just blasting cold air into my ear, okay, is equal to the number of 1 less than or equal to p less than q less than or equal to d, such that Gp is greater than Gq. So, firstly it is an inversion in the usual sense, and the other condition is that PQ, P belongs to T, P and Q belong to the T part. So, you look at the inversions, you only count inversions which belong in the T part of the set partition, that is in the fermionic part. X is a set partition, so X belongs to X mu nu. So X is this S1 union Sk union T1. Maybe, yeah. So these, if you only count those inversions which belong to the T part. Where the P and Q belong. G is a permutation. SD. G of P is greater than G of Q. P is less than Q, but G of Q is greater than G of Q. So it's inverting that. But both P and Q have to come from the T sets.
So the partition itself is not playing very big role in the actual sense.
No, it's not. Yeah, it's just the only role it's playing is it's classifying the elements 1 to D into 2 colors or something. Yeah, into bosonic and fermionic. So that's yeah. I didn't. Okay, so then you can define this. So epsilon G, and then the theorem is that U mu nu equals C of X mu nu twisted by this epsilon. So I didn't fully write down the proof of this, but I'll give you the gist of it. So I apologize for not giving references. I was just trying to work it out without looking at references, but Nishu has given me some references, and I found a lot of very nice papers on super RSK and various models using matrix ball property and this and that. So it's with symmetry and all that. So but you know, but I just wanted to do it in this way. So so the proof is roughly goes like this. So this U mu nu is ind SK SR cross SS to SD of CX mu tensor CX nu tensor sine, and this you can think of as functions from SD to CX mu tensor CX nu tensor sine, which transform under SR cross SD in a certain way. Whatever the representation H of So in general, if you have ind HGV, this is going to be f g to v such that f of Hg is equal to h times f of g. Okay, but the thing is, now you can think of a function from SD to Cx mu tensor. Now this thing as a vector space, you can think of it as x mu cross x nu, right? And you can think of a function from SD to x mu Cx mu cross s nu as a function from SD cross x mu cross x nu to C. And then you are going to take the S mu SR cross SS orbits, and you just need to specify what the values of the function are on the SR cross ST orbits, and those will correspond to these set partitions. So I do not want to really get into the proof right now, but so then if you take the union of all these, then what are you doing? You are looking at all these set partitions. So basically what are you saying? So if you want to determine one of these set partitions, you just have to say which, so for each of the numbers 1 to d, you have to say which subset it is in, right. So you can think of this set partition as a so you have, so you think, give these things numbers. So I'll give this set number 1, I'll give this set number k, I'll give this set number 1 prime, and I'll give this set number L prime. So I'll give the set Si, will give the number I, Ti, I'll give the number I prime. Okay. Now given a set partition like this, I can write down a word in the alphabet 1 to k, 1 prime to L prime. So these set partitions correspond to words. So X mu nu is in bijection with words in the alphabet, words of length d in the alphabet 1 to k, 1 prime to L prime, right. And the condition is that just that the letter I occurs mu I times and the letter I prime occurs nu I times, where I occurs mu I times and I prime occurs nu I times. And this is exactly the description of the tensor space, the super tensor space in Berel and Regev. So they define the super tensor space as the space of all words, and then they give a twisted representation of it in terms of the sign. Now these letters are actually 1 to it is a word of length d. So the positions are 1 to d, and ST acts by permuting these positions, and you just look at the inversions involving the positions with the primed letters, and that is the definition of tensor space in Berel and Regev. Right, so that is all I will say today. So there is some relation to matrix representation and so on.